Tracked vehicles can achieve higher mobility in unstructured environments with respect to wheeled vehicles because of the larger contact area between the tracks and the ground. For this reason, they are widely used in robot-assisted agricultural applications. Promising uses are targeted application of pesticides, weed control, and environmental monitoring. Pure rolling assumption is not valid for tracked vehicles. Skid steering turning mechanism always involves a certain degree of lateral slippage which causes understeering. Not accounting for slippage might jeopardize tracking accuracy of motion controllers. Modeling slippage usually accounts on complex empirical shear stress-slippage relationships. Distributed parameters dynamic models are more accurate but difficult to be used in control. In this paper we propose high-fidelity simulation models for flat and sloped terrain using distributed parameters, with both uniform and non-uniform load distributions. A novel machine learning-based method to predict longitudinal and lateral slippage using wheel speeds and gravity, validated on the MAXXII robot. A slippage-aware controller and planner leveraging a pseudo-kinematic model that accounts for slippage, enhancing tracked vehicle tracking performance. A comprehensive evaluation showing major improvements in trajectory tracking with the proposed controller and planner. In this video we uniformly sample the speed of the tracks to collect the dataset for the identification of the slippage parameters, and for the training of the function approximators. In simulation and in real experiments with the MAXXII robot. We also performed system identification using the LIMO tracked robot platform, both in the same indoor arena and on a slippery surface. Due to limited laboratory space, we collected data by executing spiral-shaped, open-loop trajectories at different longitudinal speeds. The slippery terrain was created by pouring soap on a plastic sheet laid out in the indoor arena. After the training, we obtained a good fitting of the predicted slippage parameters with the ground truth data, both for the longitudinal and the lateral slippage. In this case, because of the high nonlinearity, we trained two separate regressors for positive and negative longitudinal speed. Next, we show a top view of closed-loop experiments comparing the unicycle and the slippage-aware controllers, tracking a user-defined chicane trajectory. To assess the controller's performance, we repeated the tracking experiment conducted in simulation, using the LIMO robot in the indoor arena, under two different terrain conditions, a parquet floor and a slippery surface. We used the LIMO robot because, due to its physical actuation constraints, the MAXXII robot could not reach speeds high enough to exhibit significant slippage. We tested the high-fidelity distributed parameter model in open-loop simulations on inclined terrains, analyzing how track load distribution changes depending on the robot's relative position on the slopes. The results showed increased loading on the front section when moving downhill. In real conditions, the terrain is deformable and stiffens with the robot's speed due to increased compression. Our model captures this phenomena, that becomes more evident when the robot moves at high speed on soft terrain. Therefore, we linearly increase speed from 0 to 1.4 meters per second. The video shows that the robot starts to pitch when speed increases due to the increased stiffness in the front of the tracks. The stiffness increase is highlighted by the color of the arrows representing the ground forces, where lower stiffness is represented by the color changing from blue towards red. This simulation uses the uniform load distribution model to replicate closed-loop experiments on slopes, comparing the unicycle controller with the slippage-aware controller while tracking a user-defined chicane trajectory. Finally, we demonstrate preliminary navigation tests on uneven terrain using the proposed slippage-aware controller. The user can set a target frame, and the planner generates a reference trajectory for the controller to follow.